Okay, so we are going to do salts today. That is the main point of today, talking about salts and what they do. We did talk about during the strong acid, strong base titration that at the equivalence point, you have salt and water, and that's it. That's the whole point of being at the equivalence point, is that the acid and the base ran out equally. You have equal amounts, which is none, and all you have are salt and water. And if the acid is strong and the base is strong, you have a neutral equivalence point, which means you have a neutral salt. And you go, well, why? Well, because all you have at the equivalence point are salt and water. So the pH is 7 if both of your sources of acid and base were strong. And you go, well, what do acid and base have to do with salt? Well, acids and bases give you salt and water. Salts are a product of acid-base neutralization reactions. So we're going to talk about the relative strengths of the acids and bases that the salt is formed from to help us understand this idea. Okay, now this topic down here, the weak acids and weak bases, they can give us acidic, basic, or neutral salts depending on the relative weaknesses. So like if the weak base is a stronger weak base than the weak acid, then the salt will be basic. But if the weak acid is a stronger acid relative to the base, then it's an acidic salt. And you do that, you know those comparing their K values, whoever's bigger, but we're not going to go into that much. We're going to talk about strong, which we've already talked about, and then strong with weak. We really won't go much more into weak species, okay? So, here we go. The first thing we're going to do is we're going to work backwards to figure out whether the salt is acidic, basic, or neutral, all right? And how we're going to do that is we're going to pull the salt apart and try to figure out which base and which acid it came from, because the acid in the base gives us salt and water. So how we do that? First, how do you know that this is a salt? Well, it's a plus with a minus. Metal, nonmetal, metal, polyatomic, cation, anion. Those are salts. Anything that's ionic in this class is considered a salt. Okay, so this is what you do. You pull the salt apart. You go, okay, this would be K plus, right? And this would be Br minus. Now, I'm not going to write the pluses and minuses right now, because instead, I'm going to put my cation with OH, and I'm going to put my anion with H. So like KOH, because K is plus 1, OH is minus 1. Br is minus 1, so I'm going to put that with H plus. So KOH and HBr would give us this salt, and it would also give us water. So this base and this acid would give us this salt. Well, this is a strong base, and this is a strong acid. So this is a neutral salt. Strong will always give you a neutral salt, aka pH 7 of the salt. So KBr is a neutral salt because its source was a strong acid and a strong base. And the reason that is because the conjugate of the strong base and the conjugate of the strong acids are weak. And they're so weak that they just sit in there and they can't do anything in order to try to change anything else about the reaction. In other words, they don't undergo what's called hydrolysis. And we'll talk more about what hydrolysis is in a second. Okay. So because this is a neutral salt, it will not undergo hydrolysis. And again, I'm going to talk about what hydrolysis is in a minute. So let's try the next salt. Sodium bicarbonate. Okay, how do I know it's a salt? Metal polyatomic, ionic salt. So let's rip it apart. So here's the sodium. Here's the bicarbonate. Now I'm going to add hydroxide to the sodium. And I'm going to add the hydrogen to the bicarbonate. So instead of HCO3 minus, it's going to be H2CO3. There's 2 hydrogens now. So this is a strong base. And this is a weak acid. So before we did this, I kind of taught you a cheating way to realize whether it's acidic, basic, or neutral. And we did this during the titration problem. A strong base with a weak acid will give you a basic salt. And then I cheated and told you, and I said it's because the strong base overpowers the weak acid. Okay? And that's all you need to know for just this brief moment. We'll go back to that later. So there is a part of this salt that will undergo hydrolysis because it's not neutral. We're going to get into that last. So let's go to the next salt. Ammonium chloride. +1, -1. Ionic. So it's a salt. So I have NH4 plus and I have Cl minus. And again, I'm not writing the charges because I'm going to throw something with it. I'm not going to just leave it as NH4. So I put the OH minus with the NH4 plus, and I put the H plus with the Cl minus. So this is a weak base and a strong acid. So based on what I just told you, this is a weak base and a strong acid. We're going to predict that this salt is acidic because the acid that's strong overpowers the base that's weak. And that method of thinking works, but I'm going to prove to you why in just a moment this happens. Like, why is this salt basic though? Like, okay, yeah, it came from a strong base, weak acid. Okay, that's part of the reason, but you'll see another reason why. Because now what we're going to do is we're going to undergo hydrolysis. If you have a salt that is not neutral, part of the salt will undergo hydrolysis. So it's your job to figure out which part that is. And the part that it is the part that comes from the weak species. So when you have, for example, in part B, a strong base and a weak acid, it's not the strong base part, okay? It's the weak acid that causes this part of the salt, because that's the source, right, to undergo hydrolysis. And the reason that is weak substances have strong conjugates. So when I go to underwrite the hydrolysis, you do not use the acid. We're doing hydrolysis of a salt, not of an acid. You take that guy. This is my part of the salt, Na plus and HCO3 minus. This is my strong conjugate base from the weak acid. And it undergoes hydrolysis, aka you add water to it. Because what's in there? Salt and water. So the hydrolysis means add the water to it. Well, now it's your job to understand how this is going to behave. If this part of the salt came from a weak acid, this part right here is a conjugate base. So it's going to act like a base. So then it's your job to also know how bases act. They accept hydrogen ions. So from who? The water. If you have trouble seeing this, write water as HOH. So now this guy's going to take in a hydrogen. So you get H2CO3. And then you only have OH minus left. This equation right here is the hydrolysis of the salt. That's what this is. And look what happens. Because this is such a strong conjugate base because it came from a weak acid, remember weak substances have strong conjugates and strong substances have weak conjugates. So that's why up here, none of this happens because these are strong, so their conjugates are weak. They can't yank anything away from water. They're just like not capable, okay? Look what it produces. Hydroxide ions, which is a base, right? And you go, well, it produces carbonic acid too. Okay, Sure. But this is a weak acid. This is a strong base. So the production of the hydroxide ions is what causes this salt to be basic. And that happens because of the hydrolysis of this bicarbonate ion. This bicarbonate ion is so strong that it won't just sit there and mind its own business. It's like, yeah, I see you, water, and it yanks a hydrogen from the water. Okay. So let's look at the ammonium chloride one. Chloride. So ammonium chloride is formed from the reaction between ammonium hydroxide and hydrochloric acid. So you locate the weak species, the weak acid or the weak base. In this case, it's not a weak acid, it's a strong acid. So it's the weak base that I'm looking for because its conjugate is a stronger acid. Now, it's not a strong acid. So it's not like all of a sudden you've created one of our 6 strong acids. But its conjugate is so strong that it will undergo hydrolysis. So the ammonium ion will undergo hydrolysis, which means I add water to it. And now it's expected that you know how the ammonium ion is going to behave. Well, if ammonium ion came from a weak base, the ammonium itself is a conjugate acid. So this is going to act like an acid. So how do acids behave? They donate or they lose or they give away a hydrogen. Well, to who? To the water. There's an exchange of hydrogen ions between the 2 species. And in this case, this guy's going to give its hydrogen away and the water's going to take it. So ammonia is formed after it loses a hydrogen. And then the water takes in a hydrogen, so you end up with H3O plus. Oh, you're producing hydronium ions? That's acidic. Questions so far? We're going to do a bunch more practice before we even use numbers. So I do have a multiple choice question, and now I realize they don't ask you this in the multiple choice question, but since we're just starting, I'm going to ask you to do this. I do want you to answer it, but I also want you to go and work your way backwards, and I want you to tell me, even though this isn't part of their question, which acid and base formed these salts, all of them. Okay, so for example, NaCl. When you pull it apart, Na, Cl. The Na goes with OH, plus 1 minus 1, and the H goes with Cl. The acid and the base that makes this salt would be sodium hydroxide and hydrochloric acid, because you'd get salt and water. Okay, so strong base, strong acid, that's going to be a neutral salt. So this guy's out. I want you to take a moment, and I'm going to give you a couple minutes to try to do that for the rest of them, please. All right, so how do we do? I basically sourced out the acid and the base that formed this salt, and this salt, and this salt, and D is the one that comes from a strong acid, weak base, which is what makes it acidic. Any questions on this part so far? All right. So I'm going to have you practice now showing the hydrolysis of the salt. Be careful, or not be careful, but I just want you to notice, why is this a salt? Metal polyatomic, or cation anion, is going to be ionic. Anything ionic is called salt in here. Anything that's ionic is called a salt. So we got to get over that NaCl is the only salt that exists, because it's not. It's a salt you can eat, yes, but it's not the only salt that exists. So is this what you get? This is the part of the salt that undergoes hydrolysis because its source was a weak acid, which made this part a stronger conjugate base. And bases accept hydrogen ions from the water. And again, if you're having trouble with water, write it as HOH. So the hydrogen ion comes over here, and you're left with OH minus over here. Questions on the hydrolysis of this salt? I'm going to do a couple more. So let's show the hydrolysis of potassium nitrite. So conjugate acts like a base with water, undergoes hydrolysis, and this is what our products are. How we doing? Is this okay so far? Okay. So this is the last one, and then we're going to start working with actual numbers. Questions? Okay, so let's start doing some math with it. Aniline is an amine that's used to manufacture dyes. Okay, it's isolated as aniline hydrochloride, which is a salt. Now I want to show you something that they've done on this specific type of problem, because this portion right here is organic, and it's not expected that you know its charge. Okay, there's many cations that you should know their charges to, and this is not one of them. So what they've done is they've shown you its charge so that you can use it properly. So technically this isn't how the formula is written. What I mean by that is if I were to really write this formula, it would look like this. Okay? But what they've done is, we know Cl is -1, so what they're trying to tell you is that this entire thing is +1, because this is not like an ion you would have ever known. So that's why they have this little plus here, is to like help you, because you need to know the charge when you're going to do the hydrolysis part. Okay? So they tell you it's a salt prepared by the reaction of the weak base aniline and hydrochloric acid. So they even tell you how it's formed. Well, we know hydrochloric acid is strong, right? So like, that's the Cl is not going to be the part that undergoes hydrolysis. Okay? Now, I'm going to go off on a little tangent. So aniline is an amine, and you don't need to know this, but amines are like NH groups on organic compounds. And you don't need to know this, but it should sound familiar from biology. Amine. Where does it sound like that you've learned in biology? Amino acids, and that is true. And that is because they link up and form peptide bonds with NH groups. Okay, so that's just my little bio tangent. Anyways, they give you the Kb for aniline, which is an organic weak base. Okay, and they give you that number. So we go, okay, obviously aniline is the weak base, so this conjugate right here is going to be the part of the salt that undergoes hydrolysis. So you want to first write out the hydrolysis of this guy. C6H. This is the conjugate acid of the weak base aniline. So I'm going to write acid down here. Conjugate acid. Whatever. Still acid. So this is the part of the salt that's going to undergo hydrolysis, because the Cl comes from HCl, and HCl is strong, so it's not this part of the salt that we care about. And to do hydrolysis, what do I add to it? Water. And what do acids do? They lose hydrogen ions, right? So this guy's going to lose a hydrogen, and the water is going to take it. Okay. Well, now I want to know the pH of this salt, and I give you the salt's concentration. So let's have a little flashback. When I say a salt is 0.233 molar of the salt, it's really 0.233 molar of this guy and 0.233 molar of this guy. Like if I were to say a salt was 0.1 molar sodium chloride, it's really 0.1 molar sodium ion and 0.1 molar chloride ion. That's what it means. So I know the concentration of my cation is what I'm telling you. It's 0.233. Yes, they said that was for the salt, but it is for the cation also. So I'm going to set up an ice chart. Now water is a liquid, so we don't pay attention to it. And these guys are 0, right? Now, a big hint when K is given is that you have to let X equal something. So I'm going to let X equal the H3O plus ion, which is the same thing as the H plus ion. And everything is 1 to 1 to 1. Okay. Well, now I need to set up my equilibrium expression. So K equals products over reactants raised to their respective coefficients. So my products, oops. Okay. So now I'm going to just plug in what I have for my E part of my equilibrium. So this was X, and this is X, and this is 0.233 minus X, correct? So let's plug those in. All right. And now we know we're going to get rid of that minus X, right? Because it just makes our life easier. So hasta mañana. Okay, here's the problem. You cannot plug this in for K. This is the KB for aniline. This is not aniline. This is the conjugate acid of aniline. Aniline's a weak base, it's a product. That's not who you're doing the problem with. You're doing the problem with the salt. So you have to switch the KB to a Ka because this is a conjugate acid of the base. So this is an acid. So you have to use a Ka. You can't use a Kb. Luckily, there is a really easy equation for that. And it's this one. Ka times Kb is 1 times 10 to the negative 14. So if you know one of them, you can rearrange to solve for the other. So the Kb is given. It's 4.3 times 10 to the negative 10. Oops. So you just divide, right? I'm going to keep the whole number in my calculator. So this is what the Ka is because this is a conjugate acid. It's the acidic part of the salt. So how do you solve? Well, you multiply both sides by 0.233. And then you square root, right? Because this is x squared over here. And so something, something, something. So x ends up being this number. Well, x is my H3O plus ion, which is the same thing as an H plus ion. So now that I know my H plus, I can find pH. pH is opposite the log of H. This is a super acidic salt. 2.633. And that is likely because not only is it formed from a strong acid, HCl, but it also has a decent concentration. 0.233 is a pretty decent concentration. So a pretty acidic pH for a salt. So it says calculate the pH of a 0.108 molar solution of, no, I fixed this, sodium propanoate. Hold on one second. Okay, so the Ka of propanoic acid is 1.34 times 10 to the negative fifth. How do we know this is a salt? I see an anion with a cation, metal, polyatomic. Again, though, this isn't, so like propanoate is not like an ion that you're expected to know. So what they've done is they've shown you its charge to help you. So really, if I were to write out the true formula for sodium propanoate, it would look like this. Or you could technically throw the sodium out front. The reason they tend not to is because it's the oxygen. The sodium loses the electron to the oxygen. So they're trying to show you that that's where the sodium would be attracted to. This is the true formula. But again, when they do it like this, they're saying like, okay, sodium's +1, and this ion that you're not familiar with is -1. Because again, you need the charges to do hydrolysis. So try to do this one. See if you guys can do this one now, given the last problem. So I got this far, set up my equilibrium expression, and the question is, do I plug 1.34 times 10 to the negative fifth right here? And the answer is no. And so let's talk about why. This is the Ka of propanoic acid. This is not propanoic acid. This is propanoate. This is the conjugate base of propanoic acid. So you can't plug a Ka in for something that's a base, a conjugate base. You have to plug a Kb in. So you have to take this Ka value, use this equation, and rearrange to solve for Kb, because that is the number that you have to use for the K value. And that number is 2. Oh, no. Sorry. What is it 5 something? I don't remember. 7.46 something times 10 to the negative 10. Okay, so you go back over here, and that is what you use for K. So now we can solve for x. You multiply both sides by 0.108. And then, of course, you have to square root. And x ends up being 8.97 something times 10 to the negative 6. Well, x is my OH. So I could find POH. So if I take opposite the log of OH, which is this number right here, I get a POH of 5.04 something something something. But I didn't ask for POH, I asked for pH. So you take 14 and you subtract that number, and pH is 8.953. So a basic salt because it came from a weak acid and strong base. So I do want to bring one really important point up. You have already done this type of problem. Not today. When have you done this? So this is an important concept. Is that oftentimes when you're doing certain problems, you think it's that type of problem, but there's other problems embedded in them. So like, for example, when we did the weak strong titration, and I asked you to find, it was a weak acid and a strong base, I'm pretty sure, and I asked you to find the initial pH, that wasn't a titration problem. It was a weak acid problem at the beginning because all you had was a weak acid, okay? This was also part of that problem. You will always be doing a salt problem at the equivalence point of a weak strong titration, because at the equivalence point, all you have are salt and water. And if one of the substances is weak, that means the conjugate in your salt is strong and it will undergo hydrolysis. So we did a salt problem at the equivalence point during that titration. So every single equivalence point that we have for a weak strong titration will be a salt problem.
Have a great spring break.
Thank you.
You guys have a good spring break.